Alright, so sounds like this particular problem is giving you a lot of trouble. So let's see if we can't just kind of work through it again here, and maybe I can clear this up. I was kind of brief the other day, so I'll go through it a little slower. It says that we have 27 items that are randomly selected from a population of 275 items. Now the first thing we want to do as we go through this is we want to label, label, label. We want to take these numbers because we know we're going to have to do some, number crunching, and we want to put the variable name with them to help us kind of organize, okay? So when they say that this 27 is selected from this 275, well, what that means to us is that, maybe I'll list it down here, is that we have a population, and population, N, capital N is the letter we use, of 275 items, and from that, from that, we are selecting 27. Right? So far so good. We got that part, right? Okay, so that takes care of this sentence here. Now it says, excuse me, that the sample mean is 39. Well, now it said the sample mean, and we know that that is x bar. Now, how should I do that? Can I just type x? Will you follow me if I say x? It's hard for me to get the little bar over the top of that, okay? So x bar is 39. That means on average, but not the average of all the items selected. They came up with this average by simply looking at the sample, okay? So they, we don't even know what they're measuring here, right? Now, they also tell us that not only do they know the sample average, but they know the sample standard deviation. And this is where I'm reading it right here. The sample standard deviation, the letter we use for that is S, not sigma, but S. Now, I said not sigma, and the significance of that is that we don't know sigma. I'm going to write sigma is unknown. Okay? As you can probably tell, I paused the video for just a minute because I wanted to make sure you knew what I was talking about when I said sigma. So I went through and I added that symbol in. This is our sigma, right? But we don't know sigma. Sigma would be the standard deviation of the population of this. We don't know that. Everything that we know here, all this stuff, and I'm going to highlight that in yellow, is about the sample. Everything has to do with sample, 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 right? Sample mean, sample standard deviation, all that kind of stuff. We know this is the greater population, but all the other information is about the sample. Now they say to us that they want us to develop a 95% confidence level. Well, what does that mean, a 95% confidence level? What it means is that our sample mean is going to be dead center of the normal distribution, and half of that 95% is going to be to the left. In other words, what if our sample mean is actually wrong? Well, it could be too high, it could be too low. We really don't know, do we? So if we think of the sample mean as being kind of in the center, we could be half of this wrong to the left. In other words, 47.5 off to the left or 47.5 off to the right. Okay, that's what that confidence level means. Okay, so now they want to know, where does the confidence interval begin and where does it end? Now, there's one problem as we get ready to work this. I'm going to go ahead and use the solution that they've provided because what they're saying is that 39, which is the sample mean, right? Sample mean 39, x bar, is in the middle. So again, we can be 47.5% off to the left or to the right. So plus or minus a certain value. So now we need to understand, where did all these values come from? That's our next step. So we said that 39, the sample mean, is in the middle of the curve, and we're going to plus or minus because we can be off to the left or to the right. We can be too high or too low. So where does all this stuff come from? Well, let me start at the back and move this way. Okay, the first thing is this 275, this is our population, minus 27, this is the sample, divided by 275 minus 1, square root of that. This is called the finite correction factor. Now, in your book, about page 309, they explain this, but let me give you the gist of this. Here's that formula that we just looked at. Capital N minus little n, population minus sample, divided by population minus 1, square root. Now, you might be saying to yourself, how did they come up with that? What sense does that make? And because, you're upset, you're confused right now, just put that out of your mind for just a second. We stand on the shoulders of others. Somebody else did the calculus, did the derivation, and they're telling us that we have to use this. But because they did the derivation, we have to also be careful to use it only when they tell us it's appropriate. When is it appropriate to use it? We use it, it says the usual rule is to use this formula, it becomes necessary when the sample divided by the population is less than 5%. So you do a quick check. You go back to the problem and you say, is 27, well, let me pause this. Okay, I wanted to bring up Excel because I'm going to say 27 divided by 275 is 0.09. Okay, so what they're saying is that the usual rule is that if the ratio of the sample to the population is less than 5%, then we can ignore this formula. If it's not, and in our case, here's 27 divided by 275 is 9%, since this is greater than 5%, we have to we have to factor it in. We have to use this correction factor. Now, perhaps what you're asking is, why is this even necessary? And remember, I did tell you we stand on the shoulders of others. Well, the gist of this is that the reason it's necessary, what they're trying to show you in this chart, is if I have 1,000 employees and I just take a sample of size 10, it's going to have a lot of error in it, isn't it? I mean, if I get 10 kids in a room out of 1,000 kids and I say, what's your favorite color? Once one of them says purple, probably everybody says purple, right? So, or maybe all their favorite color is purple. But if I ask 500 of those kids, I'm probably going to find that some like purple and some like blue. In other words, I'm getting a better mix of the population, and so it's more accurate. So I shouldn't go around saying that I have a ton of error in there, because in fact I've sampled so many that I'm much more accurate. That's the purpose of the finite correction factor. So we do this little test. We divide our sample by our population. If it's less than 5, then we don't use this, but ours is greater than 5%, and so we have to apply this correction factor. Okay, so let's keep that in mind. That's why we have to use that. Now, you know, since Chapter 8, that the way that we calculate sigma, that we don't just use sigma. We're using what's called sigma of the mean, right? So, because we're working with the mean of the means. So we need to take our sigma, which is actually not sigma, is it? It's the sample. Sigma is unknown, so we have to substitute the sample standard deviation. And of course our formula says sample standard deviation divided by square root of the sample. So that's where that comes from. Now, I suspect where you're really running into confusion is, where does this 2.056 come from? Because you're very familiar with this point, at this point, with the 95% confidence interval, and you know that that does not correspond to 2.056. The reason that you're confused is because you're trying to use a z value here, and you can only use a z value when sigma is known. Well, sigma is unknown. We had to kind of cheat, and we had to use the sample standard deviation, okay? So, since we had to substitute some information. We're not going to use the Z table. We're going to use the student's T table, the T distribution. To tell you the truth, most students prefer this. They find it a little bit easier. You come over here and you look at the confidence intervals. And our problem, let me just make sure, was 95% confidence interval, right? So we looked under the 95% confidence, and so we know it's going to be someplace in this column. Now, what number do we use over here? This is DF is the degrees of freedom, and degrees of freedom is defined as n minus 1. In other words, our sample size, 27 minus 1 equals 26. So in the 95% column, I'm going to scroll down until I find 26, and this is what I use as my T value. In other words, it's not the Z value, it's the T value. Now, maybe the source of your confusion is that you're saying, where does this T come from? Well, remember that T is a little bit more of a forgiving curve. It allows, it's shorter and it's kind of squattier, so it allows for more error. Okay, the Z distribution is a little bit tighter, and so there's less error. Why is that important? Because you have extra error because you didn't know one of the critical pieces of information. You didn't know sigma. You only knew the sample standard deviation. Okay, so I hope that helps, but the thing to understand is that sigma was unknown, so we had to use the sample standard deviation, and so we used the T table. I hope this helps.